Okay, welcome. Today we're going to start talking about Fibonacci numbers and the golden ratio. A famous and important sequence is the Fibonacci sequence, named after the Italian mathematician known as Leonardo Pisano, whose nickname was Fibonacci, and who lived from 1170 to 1230. Now, this sequence is created by taking the first two numbers, which we always start with 1 and 1. We add those to get the third digit, a third number in the sequence, which is 2. And so we're always adding the previous two numbers in the sequence to get the next number in the sequence. So 1 plus 1 equals 2, 1 plus 2 equals 3, and so on. So we have 2 plus 3 will give us 5. And then 3 plus 5 gives us 8, and then so on and so forth. 8 plus 5 is 13. 13 plus 8 is 21, and then 34, 55, and then 89, and so on. Okay, the Fibonacci sequence is defined recursively. This means that each term is calculated by a formula involving previous terms in the sequence. So more precisely, the Fibonacci sequence is defined by the recursive formula that is f sub n equals f sub n minus 1 plus f sub n minus 2. So in other words, we're taking the previous two numbers in the sequence, adding them to get the next number in the sequence. And this works for all integers n greater than or equal to 3. Okay, where again we define the first two numbers in the sequence equal to 1. In other words, to get the next term in the sequence, add the previous two terms. So let's calculate a few using f sub 1 equal 1 and f sub 2 equal to 1. And so here we go. So f sub 3 equals the first two, so 1 plus 1 equals 2, right? And then f4 is f3 plus f2, which is 2 and 1, which equals 3, and so on. Okay, and we can keep doing this over and over again. Now, let's do an example. Given that the 13th and 14th Fibonacci numbers are 233, 233 and 377, use the recursive definition to find the 15th one. So all we have to do is just add these, which would be 610, right? So 610 would be F15. Calculating terms of the Fibonacci sequence can be tedious when using the recursive formula, especially when finding terms with a large n. Luckily, a mathematician named Euler, which we've talked about before, discovered a formula for calculating any Fibonacci number. This formula was lost for about 100 years and then was rediscovered by another mathematician, by Jacques Binet. This is now known as Binet's formula and is shown below. So Binet's formula tells us that the nth Fibonacci number is given by the formula f sub n is equal to 1 plus the square root of 5 divided by 2, quantity raised to the nth degree, the nth power, minus n minus the square root of 5 divided by 2, quantity raised to the nth power. And that quantity is the numerator, that difference is the numerator, and we divide that by the square root of 5. Binet's formula is an example of an explicitly defined sequence. This means that the terms of the sequence are not dependent on previous terms. A somewhat more user-friendly simplified version of Benet's formula is sometimes used instead of the one above, and that is given by this formula here. And so we take the quantity 1 divided by the square root of 5 times the quantity 1 plus the square root of 5 divided by 2 raised to the nth power. Okay? And then we just round to the nearest integer. Now, to understand why this formula also produces the Fibonacci number f sub n, we look at the second exponential term in Benet's formula. So right here. So the base of this exponential formula, or this expression here, which is this, is approximately equal to negative 1.618. Since the base has a magnitude of less than 1, raising it to a power of n produces numbers that quickly approach 0. And so this is illustrated by the table given here. Okay, so as n increases, this exponential is going closer and closer to 0 quickly. So as n grows, the second term is vanishing. And so n f sub n approximately equals this. Okay, so that's why this term here is going to 0, right? So for large values of n, we can approximate the nth Fibonacci number in the sequence by using this one. Okay, so that's why it works. Okay, moreover, from the table, we can see that the error is always less than 0.5, right? Much less. And so rounding to the nearest whole number will always yield the exact value of n. Okay, let's see here. Let's do this example here. It says calculate f of f sub n using Benet's simplified formula. So what do? We just take this formula and we just plug in 10 for the exponent, and we just plug in chug. And so we get approximately 55.00. So the answer is going to be 55 by rounding to the nearest whole number. And so we're done. And here's the calculator check to show that we did it correctly. Okay, so we can always use the simplified Benet formula. Let's do another one. So here's another example. So let's do 19, and we're going to use Benet's simplified formula again. So again, all we do is we just plug in 19, use our calculator, plug in the values, and what do we get? We get approximately 4,181.00, so we round to 4181. Okay, we can verify that with the calculator. And then again, if we do 40, right, all we're going to do is just plug into the simplified formula, and the calculator is going to give us something approximately equal to this, right? And the decimal is going to be extremely small, so we just round. And so this is f of 40, or f sub 40, I should say. Okay, so not bad. I mean, it's pretty straightforward. Now, we can also observe many examples of Fibonacci numbers in nature. For example, the number of branches on certain trees or the number of petals of certain flowers are often Fibonacci numbers. Okay, look at the petals on a daisy. So here's a petal with 13, daisy with 13 petals. And then we've got a daisy with 21 petals, which are both Fibonacci numbers. Okay, then we can also look at spiral growth, right? Fibonacci numbers also appear in spiral growth patterns, such as the number of spirals on a cactus or in sunflower seed beds. So if you look at the cactus here, look at the number of spirals. Okay, here we've got 13 clockwise spirals. Okay, we can see the spirals right here. So there's 1, 2, 3, and so of course we can go all the way around and we count 13, or we can count the spirals in the sunflower seed bed, right? So if we look at the clockwise spirals, right, we can count 34 if we go all the way around. If we look at the counterclockwise, we got 55. Both of them are Fibonacci numbers. Pretty interesting. Another interesting pattern arises when looking at the ratios of consecutive Fibonacci numbers. This is where I think it gets pretty cool. So if we look at this, right? So 1 over 1, 2 over 1, 3 over 2, and so on. Look what happening to the ratios. 1.6, 1.625. So what's happening to these ratios, right? Well, as we look at the ratio, right, the 1 number is going towards 0. The other term in our Binet formula is approaching 1.618, which we saw in Binet's formula, right? And we can easily explain this limiting value of these ratios by the simplified version of Binet's formula. Okay, so look at this. Oops. Okay, if you look here, if we do a little bit of algebra, right? And so if we do the ratio, so we take the ratio of any two consecutive Fibonacci numbers, right? So f sub n minus n plus 1 divided by f of n, right? And then we simplify it using algebra. What happens is we get one of these out. And so we get this. Okay? So the value that these ratios are approaching is a special number called the golden ratio, which is denoted by phi, the Greek letter phi. The golden ratio is the number phi, which is 1 plus the square root of 5 divided by 2. So the approximate value of the golden ratio is 1.61803399. It goes on, but that's the approximation. This number was studied extensively by the ancient Greeks, and it was thought to have a special significance. They called this the divine proportion, and it was used in both art and architecture. It is claimed by some to be the most pleasing ratio to the eye. To find this ratio, the Greeks cut a length into two parts and let the smaller piece equal 1 unit. The most pleasing cut is then the ratio of the whole length, x plus 1, to the long piece, x. Okay, so let me say that again. To find the ratio, the Greeks cut a length into two parts and let the smaller part, the smaller piece equal 1 unit. So here it is. So this would be 1 unit. The most pleasing cut is when the ratio of the whole length, x plus 1, to the long piece, x, is the same as the ratio of the long piece, x, to the short piece, 1. Okay, so how would that look? So it would be the ratio of the whole piece, so x plus 1, to the long piece, x, is equal to the same, equal to the ratio of the long piece, x, to the short piece, the whole piece, x plus 1, to the long piece, x, and is the same as the ratio of the long piece, x, to the short piece, 1. Okay? And so when we take that and we simplify it, we get what? We get this equation, solving this quadratic equation equal to 0. And of course, in order to solve this, it's not factorable, so in order to solve this, we have to use the quadratic formula, right? And so voila, look at this. We get two values of x. The golden ratio is a positive number. So that means what? Okay, so it has to be a positive solution. So it can't be this one. Okay, so meaning it has a property that x squared equals, or excuse me, not x squared, phi squared equals phi plus 1. This means that if you want to square the golden ratio, just add 1 to it. It can also we can also verify this by plugging in phi. Right? So if you plug in phi, we get this. Doing the calculation, you could see that both sides rounded to 3 decimal places are equal to 2.614, or excuse me, 2.618. Another interesting relationship between the golden ratio and the Fibonacci sequence occurs when we take powers of phi. So if we take powers of phi, let's take this, right? So phi cubed equals phi times phi 2, which equals phi times phi plus 1, right? All we're doing is using this, right? This equation. And then we get phi squared plus phi, which equals phi plus 1 plus phi, which equals 2 phi plus 1. So we get phi cubed equals 2 phi plus 1. So if we do 2 phi to the fourth, we do something similar, and what do we get? We get 3 phi plus 2. So phi 3 equals 2 phi plus 1, or phi cubed equals 2 phi plus 1. Gosh darn it. Phi to the fourth equals 3 phi plus 2. What happens when we do phi to the fifth power? Well, we get 5 phi plus 3. Notice what's happening here. We get 2 plus 1, and then 2 plus 1 equals 3 plus 2, which is this one. And then we have 3 plus 2 equals 5, and then we have this one. And then next one is 8 plus 5. So what would be the next one? The next one would be 13 phi plus 8, right? And then 21 phi plus 13, right? And so on. So notice that the coefficients on phi and the numbers added to the phi term are consecutive Fibonacci numbers. This can be generalized to a formula known as the golden power rule. And so the golden power rule says phi to the n phi to the n is equal to f sub n times phi, so the nth Fibonacci number times phi plus f sub n minus 1, okay? So now what we can do is powers of the golden ratio. Let's do this example. So now let's use this to find phi to the 8th power. So the 8th Fibonacci number times phi plus the 7th Fibonacci number. And so the 8th Fibonacci number is 21 and is 13. So we take phi, which is approximately 1.618, times 21 plus 13, and that gives us this. And then if we do it for 11, or excuse me, for 15, do the same thing. We take the 15th Fibonacci number, 610, times phi, 1.618, plus the 14th Fibonacci number, which is 377, and we get 1363.98. So again, pretty straightforward. And that finishes up this section. Have a great day.